Hey guys, good morning. I'm here early getting ready for the day. I'm about to go back home and take care of my little girl. She still has the stomach bug, so you can pray that she gets better today and that the rest of us don't catch it, and hopefully I'll be back with you tomorrow. Thank you for your great behavior this week and for working hard and getting those assignments turned in even when I haven't been here, and I apologize for that. But I hope you have a great Wednesday today, and I'm going to make you a short video of notes to take, and those are going to be in your notebook, and then you'll have a worksheet to do based on those notes. Please send me a message on Remind if you have any questions, and you can get to Remind on your computer if you need to, or you also have permission, as long as you let Ms. Hussein know what you're doing, to have your phone out for just a second to send me a Remind question as well if you happen to get stuck. And she has my number too. If y'all have any questions, you can send them through her as well. All right, so we're going to get started. You need your notebook. We're going to be on page 14 in your notebook, and on page 13, we're going to do our metric mania. So leave page 13 blank. I know there's nothing there right now. But on page 14, we're going to start with our motion notes. So I'm going to go through a PowerPoint, and you're going to take notes on page 14. Now, the beautiful part about a video is that you can pause the video. So if you need to get your computer, if you're sharing with someone, feel free to get your own. There's headphones under the sink, and there's also headphone jack splitters. If you need to share a computer, you can both still have a pair of headphones. But please, please pause the video to make sure that you get the notes that you need as we go through this. All right? So what we're going to be looking at is motion. Right, motion. And so yesterday you looked at that sum and y'all did the activity online. And so today we're going to look at some more specifics in terms of the equations that we use and the definitions that we want to make sure that we have. All right, so here we go with motion. All right, here's the definition. Motion occurs when an object changes position relative to a reference point. So yesterday, you had the man standing in the middle, and that was called 0. That was set up as our reference point. All right, so that's what motion is, when an object changes position relative to that reference point. All right, we don't have to see something move for motion to take place. It just has to be somewhere different than it was before. Of course, we know it moved if it's somewhere different than it was before, but motion is not something that we have to necessarily see with our eyes. All right, so make sure you get the definition of motion in your notes, and you want to underline or bold, circle that reference point. That's going to be our 0. All right, 2 key terms, and hopefully you got an idea of these yesterday, but distance describes the motion. And it tells us how far did the object move. How far did the object move? Okay, and the unit for that is going to be in meters. However, displacement is a little bit different. So displacement is your distance, but also your direction. And displacement tells us the change in position. So if you looked at that yesterday, you noticed that distance to the, I think it was the tree, was like 8, but the displacement would have been -8. So displacement has a direction and a numerical value. It is also in meters. So it's basically the same as your distance in terms of the unit, but displacement can be negative because it has a direction. Okay, there's something else a little different here too. If we look at this image, this gives us an idea of the difference between them. So let's say you're coming to school, and if you were a bird and you could fly, you could just go to school like on a straight path, right? But we have to take the road to school. So it goes out here, then we turn down 78, then we turn off, then we turn on Viking Drive into school, okay? So you see the difference. The displacement is just the how far are you from where you started. So that's going to be your short distance between where you started and where you are now. But distance is how far did you go. So that would be how far did you go in your car. And then displacement is how far are you from your house, like on a map. If you were a bird, okay, you could get there in a straight line. How far are you? And then how much did you move? That's distance, okay? So those are the differences between those two. Distance, how far did you move? Displacement, how far are you from your starting point? Both are measured in meters. Displacement can be negative, but the other cannot. All right, speed. You looked at a few different speeds yesterday. Speed is the distance an object travels per unit of time. Speed, the equation, is distance divided by time, or S equals D over T. Make sure you have this definition and equation in your notes. The unit we're going to use for speed is meters per second. Now, obviously, we can measure speed in other ways, like the speed of our car in miles per hour. But it's always going to be a distance divided by time. So in our car, we do how far in miles and our time in hours. But in physical science, most of our measurements are going to be in meters and our time in seconds. All right, so there's that equation again. Speed equals distance, so we have the ruler on the top to represent that, divided by time. Now we can rearrange this equation. If you think about algebra, we could solve for the distance, we could solve for the time. So let's look at that on the next slide. All right, make sure all three of these are in your notes. So speed equals distance divided by time, but we could also solve for time. Time equals distance divided by speed. Or we could solve for distance equals speed times time. All right, so those are the three equations we need in this section. If you want to solve for speed, use that one. If they ask you how long did it take, time. And if they ask you how far did they go, distance. All right, so let's do these three practice problems together. Make sure you have them worked out in your notes. If a car travels 400 meters, that's our distance, in 20 seconds, that's our time, how fast? So we're looking for speed. So speed, and I want you to write yours out like this on the practice problems today. Okay, make sure you show your work. Speed equals distance, so that's going to go on the top, 400 meters, make sure you include that unit with your numbers, over 20 seconds equals, all right, 400 divided by 20 is 20, so 20, and make sure you have units on your numbers, meters over seconds, or meters per second. All right, so that's an example of solving for speed. Again, any practice problems you do today, make sure you set up your work and show it like this. Number 2, how long did it take you to walk 100 meters? How long, we're looking for time here, how long did it take you to walk 100 meters? There's a distance. If your speed is 2 meters per second. Right, well, let's see, time equals distance, 100 meters, divided by speed, 2 meters per second. Right? 100 divided by 2 is 50. Notice what happens here. The meters are going to cancel each other out. Anytime you have a unit on the top and the bottom of a fraction, those can cancel. So we're just left with seconds. And that makes sense, right? It took 50 seconds. So you want to make sure your unit makes sense with the question. How long did it take? It took 50 seconds. All right, last example here. What is the distance traveled? So we're looking for distance now. If you walk 1.5 meters per second, there's our speed. In 45 seconds, there's our time. We're looking for distance. So distance equals speed times time. There's the equation up there. Speed times time. So 1.5 meters per second times 45 seconds. So we can do that. I'm going to have to use a calculator for that one. 1.5 times 45. That's 67.5, or we can round that to 68. Notice here, seconds are under the fraction, and there's seconds right there, so they can cancel. 68 meters. What is the distance traveled? It is 68 meters. Okay, so that answer makes sense. Right, so there's an example of solving for each one. So you can use that as you're doing your work later today. Come back to those. Make sure you have your 3 equations. All right, we can also get this same information from a graph. So if we look at this graph, we have distance along the y and time along the x. So let's go back to thinking about distance and displacement for a second. Distance is how far you traveled overall. So first, this guy went 5 meters. Then he went backwards from 5 to 1. So that's 4 meters. So 5 meters. And then he went 4 meters. And then he went back this way from 1 to 3. So that's 2 more meters. And then he went this way from 3 to 2, so that's 1 meter. All right, so how far did he go overall? He went this way for 5, back for 4, this way for 2, this way for 1. So 5 and 4 is 9, 11, 12. He went 12 meters overall. All right, so that would be his distance. 5, 4, 2, 1. Notice he's going in different directions, just like you would in your car, but he's traveling this whole time. And then his time along the x-axis is 20 seconds. So 12 meters divided by 20 seconds. And that's 0.6 meters per second. All right, so that's distance. Now I'm going to switch colors and we're going to talk about displacement. Okay, a little bit different. Sorry that I'll erase. You can rewind if you need to see what I did before. Displacement is just how far are you from where you started. So he started at 0 and ended at 2. So his displacement is only 2 while his distance was 12. Okay, notice the difference there. Distance is how far did you move, and displacement is how far are you from where you started. But to calculate speed, we do distance divided by time. All right, so average speed is your total distance divided by your total time. So on average, how fast did you travel to Atlanta? So you'll do the total distance to Atlanta divided by the total time it took you to get there. But there's something called instantaneous speed, and that is the speed at any given point. So on your way to Atlanta, you may have been going 85 at some point, your instantaneous speed, and then you may have been going 20 at some point if you got in a lot of traffic. That's again another instantaneous speed. But your average speed may have been around 60. Okay, so on instantaneous speed, again, just take some notes. This is your speed at any given point, and that's when you look at your speedometer. Your average speed is, the speed is changing. It's overall what was your total distance and your total time. All right, velocity. Now, velocity is a little different than speed. Velocity is speed and direction. Okay, so we measure it the same way, distance divided by time, just like we do speed, but the difference is that velocity has a direction. Okay, so make sure you note that. That's the difference between them. Velocity has a direction. Okay, so we can be going 3 meters per second as a speed, but 3 meters per second to the north would be our velocity. Or negative 3 meters per second if we were going to the south. Okay, just like yesterday, you saw your man moving backwards or forwards. So if he moves backwards, that would be a negative velocity. Forward, a positive velocity. All right, you also looked at some graphs yesterday, so I want to show you these and kind of go over the meaning of them. If you can sketch this and label it in your notes, this would be very helpful. So we have distance along our y-axis and time along the x. All right, let's look at the red line first. This is 3 different scenarios. So on the red line, the person is going up about 2.5. Okay, and they're going at a steady speed. I know that because this is not a curved line, a steady slope. Okay, so a steady speed, and then they stop at 2.5, and they just stay there for 1 second, 2 seconds, 3 seconds, 4 seconds. So when we see a flat line on the distance graph, that tells us that the distance isn't changing. So the person is just sitting there. And then we see them return to where they came from. So now they're back at this 0, at this reference point. Okay, so like yesterday, this could have been the man walking forward, standing still, turning around, and coming home. Right? But the speed is steady because there's no curves. All right, then on the green line, we have the person moving pretty fast because this is going up a lot faster than the red, but it is steady because it's a flat line. All right, and then in the blue line, we have not going up as fast, so moving kind of slow at first, but notice this is a curve, and they're getting faster and faster and faster. But the green, they're going the same speed the whole time because that line is flat. All right, last thing we're going to talk about today is acceleration. Now, we always think of acceleration in like the way we use it in the English language. So I kind of want you to throw that away. Acceleration is a change in velocity. So acceleration could be speeding up. That's the way we usually think of it. But acceleration can also be slowing down or changing direction. Okay, all 3 of these are acceleration. Speeding up, slowing down, and changing direction. Because remember, velocity is speed and direction, and acceleration is change of velocity. So we can change our speed by speeding up or slowing down, or we can actually change our direction, and that would be accelerating. Acceleration can be positive, or it can be negative, just like velocity and displacement. The unit is meters per second squared. Meters per second squared. All right, so in our 2 images here, we always think of race cars accelerating, and they are because they're always changing direction as they go around that loop. But you can also be accelerating when you come to a stop. And some people call that decelerating, okay, but it is a change in velocity. All right, so what's the formula? We're going to do some math with acceleration today too. For acceleration, it is the change in velocity. So you have your final velocity minus your initial velocity divided by time. So let's say you start out at 0 meters per second. Okay, so you're at the start line, your car's ready to go, and then they wave that flag, and we'll say 20 seconds later, you're moving at a speed of 140 meters per second. Okay, just for example. So you start out at 0, your car stopped, and then you speed up to 140 meters per second in 20 seconds. So let's see how this acceleration formula works. So acceleration equals your final velocity, 140, meters per second, minus your starting velocity, 0 meters per second, divided by your time. Took you 20 seconds to do that. Right? So 140 minus 0, that's 140, divided by 20 is 7. So your acceleration would be 7 meters. Now, this second right here is under the fraction, and so is this one, so they can't cancel. So they come together to make seconds squared under the fraction. Okay, so that's where our unit for acceleration comes from. Acceleration in this case would be 7 meters per second squared. If you're slowing down, your acceleration will be negative. So let's say you went from 140 to 0. You had to stop. So then your acceleration would be negative. Alright, that is all that I have for today. I want you to do the worksheets. Go back in the notes if you missed anything. Make sure you get all of the definitions and all of the equations. And then complete the worksheet. Be sure to show your work, okay, just like I did on my example problem. And go back and look at those if you need to. Hope you'll have a great day, and I really hope to see you tomorrow.